All right, so we finished up homework 3. Next step is quiz 3, so module 3 quiz. The question is, there we go. What did we learn? Like what kind of skills, what kind of concepts? And then the next part is what are questions that demonstrate those kind of things. So once we identify what we're trying to show we know, then we'll find like a couple of questions, some examples, and then I'll build the quiz and send it out on Husky CT. I like note cards, just like something, that's all you need, right? Like a bar napkin or a note card to get started. What kind of concepts are we working on?
I'm struggling. Alright, is it you need to do like the matrices? There's some like there's some like I'm just looking into it. Yeah, I can't. Unless you just arbitrarily define. Okay. Alright. Here. Unless you just arbitrarily define where mutation becomes significant, or like a speed where mutation becomes significant. So what you determine is like some matrix. I don't know. Trying to figure out what that would be. What are the equations? Actually, it's pronounced like it is pretty because it's all back. It's all. Oh, you mean because it's like. Moment is like it is the moment. I think so. I think yes. Moment is like it ends up the chance indication curve is like yeah, it looks like that. Like it increases a logarithmic thing, and then I think that's the shape of it. Yeah. And then. And for some reason that ends up decrease like the speed of rotation decreases slower when you take into account mutation as opposed to when you don't, which doesn't make any sense. Okay. Yeah. We can take a look after. Yeah. Okay. Alright. Brush up. Because I know I've done it. I've gone through the whole thing. Yeah, exactly. So, okay. Like those so far.
So far I've seen like equations of motion, kinetic diagrams. Anything else? Frames? What do you mean by frames? Which kind? Working with frames. Yeah. So like, yeah, I'm thinking of like frame of a picture, or yeah. What kind of like what kind of frames were we working with? What was like? Does anyone remember what the different? We definitely talked about like frames, but what kind of frame was it? Yeah. Our reference frames? Yeah. Our reference frame. So reference frames, that could be like a whole coordinate system, right? So the reference frame is sort of like what are you defining as zero, and how are you measuring positions and velocities and all of that, right? So in here, this is kind of like your coordinate system, your origin, so really it's just like defining like what is motion. Like if you measure motion, how do you define that? Like if something goes to zero, where is it? There is no like absolute zero position of the universe. I guess except for the Big Bang. Maybe there was like a single location where every point in the universe was at one point in time, but and then it exploded. As far as we know, we don't even know if it really like started off that way, because all of our theories kind of break down within the first minute of like predicting backwards to the beginning, what we think is the beginning. And part of that might be our Newtonian dogma along the way, right? Like we're assuming that there's a cause and effect for everything throughout the history of time. Is there? I don't know. No one was really sure. We had like 60% of the class, so it was like by the end of the discussion, did not know whether or not free will or mechanics existed. Like, is everything cause and effect or free will? All right, sorry, that was a tangent. What other concepts, skills? Did we work on anything else? I saw these as I was walking around. Yeah. Our polar, yeah. So like this coordinate system, we looked at both Cartesian, like multiple Cartesian coordinates, and then we also looked at polar or cylindrical. We're doing 2D, so whether it's a sphere or a cylinder, it's the same thing. You end up with the same equations. Nice. Did we miss anything else? Done? Okay. All right. So a single question might not capture everything we worked on, but what are some highlights? Like what's something that you're ready to demonstrate that you think would highlight like some of these concepts or skills? That's our next step. So what question could we ask?
We could look at like what if you change where their mass is, move it up, and move it down. That's like us, that's how skateboarders get up the ramp. And maybe it's certain points. Well, so they can't like head speed, you change where the center of mass is. Increase angular velocity up around the ramp. So that would be it. Yeah, the graphs are way down, stays up all the way up. Changing where the mass is, at speed. Yeah, just for like the floor. Yeah, your angle stays. Okay. Yeah. That one was like 2 years. Right. Yeah. A lot of stuff. Okay. Yeah. Is the EAA, is it so even if it doesn't change, it's a big deal. That's like one of, I think it's one of the goals. If you can make sense of like calculation equation, then so there's all these other applications that pop up.
And it's helpful, like there's ways to quickly, like, we're always going to be the same.
Yeah.
Like, it's only going to be like some variations that those equations that you have to figure out.
Yeah.
multiple system too.
Okay. Are you thinking that it's plunging towards something that's spinning really fast? Or
Just when they would kind of maintain like this linearity, but then they now have to also go against the other forces that come with that motion. The spinning of a thought, I didn't think of.
oh, for spinning. Yeah.
I didn't think about that, but that could work as well.
All right, so I'll do like, look at, so one thing came up of like come up with what are equations of motion for these two systems, like what are the, what's similar, what's different, or like that could be one question. Another one, I'm gonna kind of try something like that. I'm imagining almost like a, have you been on those like carnival rides where you're in a chair and it swings around in a circle of like, well, that one, those are like the, oh my god, what are they called, like the mind exploders or something, I forget, but you like, you spin so fast that you're stuck to the wall. I'm thinking more like you're in like a chair on a swing set, and as it spins it starts like the whole, everybody gets sent off to the side. That's what I was thinking of. So it's like a swing that's rotating and something like that, and looking at like, and if we call this let's call it omega, like big omega. So you have like rotational system and also something like that. Did anything else come up? Oh, and then, sorry, I also saw, like this one was pretty similar to, I don't know if there was something different, because I just kind of saw it. Was there something different you were thinking about for like block on a ramp, like something on a ramp, trying to find that equation of motion or anything? Or another like slight variation. Trying to get rid of that. We could say what happens if it's a block on an incline, but it's not a spring holding it, but a damper. So the faster it moves down the ramp, the more force that damper is applying. It could be another kind of variation there. Anything else come up? What else were you looking at, thinking of? Yeah.
This is more a variation, but if you have the block on a ramp, you could actually make it a reference frame problem by saying like the ramp, like you solve for angle position of the ramp moves, angle the ramp moves, and then you have to figure out the reference frame.
Oh, so like, so if this is, I know last time we called it theta, but I'm gonna call it alpha, so we know it's just like, it's not a, so So you're saying like if this whole thing starts off like this, but then like rotates, what would happen?
Yeah.
Or even one typical thing in engineering that happens all the time is like in this reference frame, it makes sense to say like my x coordinate is the ramp. And it's like, okay, yeah, now my equation of motion, everything's kind of parallel to that. But as an engineer watching it go down the ramp, like it might be hard to measure distance along that one. You could probably find like a distance along the ramp, but if you were trying to figure out like how fast is it moving to the right, like if it's a mechanism that is changing something, like if you need to know this speed, what is that? So you can create an equation of motion. You can figure out like, okay, that I know what's going to happen along frame X, but all of my measurements are going to be, the thing that I care about is along frame like X prime. So that might be one way, is like solve for velocity. And in this case, if we have like a damper like that, velocity should reach some kind of steady state value, right? Like acceleration at some point will be 0, but it's going to keep moving because gravity and drag and the damper will be equal opposite. So then we could figure out like what is that final velocity? How fast are we moving forward instead of down? And there's a nice like connecting reference frame. And calm down. I know it's too exciting. Everyone's like jumping out of their seats. Like, oh, this is so great. Oh man, I can't believe we built this together. There's so many great ideas. One at a time, one at a time. Jeez. So how do we feel like preparation wise? Like we've all gone through some process, kind of made some equations, looking at diagrams and all this. How about did I miss anything? Did anybody feel like they wanted to add a different option? All right, so we've got kind of like A, B, and C of like different, and generally these are kind of, there'll be similar like free body diagrams and reference frames. Not all the same problem, but like A has kind of one general approach, at least that we've used. B is a different approach, but it'll have its own kind of thing. So how about A, like thumbs up for like I am prepared, ready for it, I know what's going on. Thumbs up. Cool. All right. How about B? Do we have like thumbs up, you're ready, a little iffy, a work in progress, right? Like maybe I could figure it out, but maybe need some help. How about C, thumbs up, or a little like maybe this one's somewhere in the middle, some yeses, some like definitely I got this. Do you want to try like starting either A or C? It sounds like A or C was a little more like we feel a little more prepared for it. Do you want to try like starting it and see where it leads? Okay. Which one? A or C? C? All right. Let's see where we go. How do you start it? What do you even do? Free body diagram. Yep. Yeah, main starting point is always what is your free body diagram? And to figure out your kinetic diagram, you need some reference frame. Like you have to have some definition of like, what is my 0 point? Where is this thing? What is motion in my reference frame? So we need a reference frame and we need that free body diagram, and then we can have what is our kinetic diagram. Is it a frictionless slope? What do we think? Is friction, so a better question is usually, at least for engineers, because like, for engineers, the question is not so much, is it frictionless? That's more of like a physicist, like, is it in deep space or something? Like, is it some weird application? So for engineers, it's kind of like, is friction a dominant force? Is that the thing that's driving the motion of this thing? I mean, maybe initially, right? Like there might be a point where this thing's not going to move at all because there's just enough friction to prevent motion. But if the slope is big enough and the damper is there, damper is probably the bigger force, like by a factor, usually by factors of 10 or 100 or something. So initially, we could say friction, maybe it's there, but we can say that it's not a dominant like driving force. But that's up to you. You can also just like include it and see what happens to it. That one is some constant times velocity. dampers, the unit ends up being kilograms per second. Oh, it's independent of normal force. Like, the only thing that the damper. Yeah, it would just be like B times downward, like whatever velocity it's moving at. Oh, yeah, it would just be like B times B, not B.
Why would you let the motion of the difference in other direction, how would that sort of speed?
At least, I guess it depends on where your damper is attached. If it's parallel to the slope, then the only thing that matters is like how much you're opening it.
Yeah.
But if you have something like a car suspension, it's opening as it goes down that angle,
Then at the what?
then you would have like a component of that.
Yes. All right. I see.
Yeah. All right, this was kind of an interesting interpretation. There was also the idea of like, what if we had this damper mounted to a wall, but our block is still moving like down a ramp, so that our force is always left, right, but our block is moving along the ramp. That was just another kind of similar. It would be similar equation. Like, it doesn't really change equation of motion, at least the mechanics of it, but it takes some of the component of that damper out of play a little bit, right? Because some of the damping is lost from that vertical motion. That would be kind of cool. Interpretation. I just ran out of room. All right, so I saw normal force, I saw damping, and I saw gravity, kind of like that. And then also some people drew like friction in there. I'm just saying damping is much bigger than friction. So maybe it's there, but maybe friction is kind of like, weep. Like just a tiny little arrow. It's not a significant thing. Like a well-oiled machine kind of working. What did the kinetic diagram? This one I saw a few different things. Is it this? MA up the ramp? Possibly. Is it this? MA down the ramp? Probably down. Probably down. How do we, what defines like where MA should point? Like what should a positive, if we say we are accelerating in a positive way, where are we going?
In the direction of velocity.
In the direction of velocity. Okay, so which way, what's a positive velocity? One that's increasing, yep, but where does it go if it increases? Okay, and so what I'm getting at here is like, your frame of reference is what you define as, it's totally fine to say this is a positive acceleration, but what you've done there is you're saying your frame of reference is, this is your x-axis and that's your y-axis somehow, right? Like somehow you're saying going up the slope is positive and down the slope becomes negative. Again, you can do that. I think in the homework we just said like positive x is down the slope, so positive ma is down the slope. And that's what your kinetic diagram is doing. It's just saying like, if things are positive, this is where you're going. Like a career map, just like, I got the job, I'm going to the career. Just, it's a map, just an orientation of like where everything is. So if that's x and this is y, then that's MA. And this one, so then like defining the damping force, we did it once in homework 1, talking about like, okay, let's look at a spring, let's look at a damper, we'll look at friction. In this case, it's always equal to like some constant times, I'll call it x dot, or b times v. So it's, and that is the force. Just like, it doesn't depend, it's not like dependent on normal force or anything. The general idea of a damper is that you can push a fluid through some kind of mesh filter, and the faster you move that filter, the more force it applies on your thing. So that's how like suspension works, even like door, like swinging motion slows it down with these kind of like fluid dampers. You can have like electromagnetic dampers, those are pretty cool, but in general they all kind of work as like first order, be some constant times velocity. Do you know how to get equation of motion from there? What would that one look like? Yeah. Yeah, like some. Something like this, of like whatever my x component of mg is minus that damper. Bless you. Cool. Seems like kind of ready, right? You feel good? We're demonstrating some principles, engineering principles. We know how to do it. We're ready for it. And like pausing for just silence for questions are kind of like comments. What are you thinking about? I'm fine. This seems like a pretty nice like collection of skills and concepts that we're kind of working on. Like identify a problem. What is its motion? Like define the motion. What is your frame of reference? What is acceleration? Figure out the equation of motion like with that free body diagram. Like here's MA, here are all the forces. And then from there, we could go on to like ask other questions. How would you find like will this thing, all right, so let's start with one question. Will this thing ever stop moving? Eventually? At least from our model, from our free body diagram.
Then you're saying it's slowing down with it? No.
It shouldn't move, it shouldn't stop?
Okay, so it keeps slowing down, will keep speed, but the damper will keep exerting a greater force.
Okay, yep. It should stop. Yeah. So you think, yes, stop. What do you think?
I think eventually it'll hit terminal velocity unless the damper stops it just by max extension.
Yeah, so there's one like limit of like our damper can only be so big, right? Like we can only have, but we could basically like put a block on a ramp in the ocean and just have like miles of this ramp, and we're basically created a damper of like a block sliding through water, and so now we have saltwater damper, and we could put a mesh cylinder through it or something. So we could, if we wanted to, we could have this thing move forever, but we do have a physical limit of like sooner or later you can't reach position infinity. But that one's more like in the real world. What about from our model world, like from the model, like just from the math that we're writing down here? Will this thing come to a stop? Like will position reach like a final position? No? What do you think? Final position? Some head shakes, no. No? Yeah.
You have a point in the equation of motion where it's just like a position. So there's no way position will be zero, but acceleration can be zero.
Yeah, so we can get to the point of like acceleration is going to be zero at some point. So we could say like at steady state, SS, steady state, MA equals 0, which is equal to our so in this case, B times V is like whatever that mg component is. So I'm just writing it as like a dot I to say like it's either a sine or a cosine. It's got to be like one of those components. So V will reach like some number. So if you start off accelerating and then you reach a constant speed, do you ever stop moving? Not, at least not in your model. Like your model's only limited to like, if your damper is 30 centimeters long, then really you can only move 30 centimeters, but yeah, so somehow you'll like bottom out. And that's usually what happens in suspension systems. It's like there's some bottoming out. Like, they're only rated to like 100 millimeters or 150 millimeters. Yeah. Anyway, but that's all the stuff that from there, like, but the core thing is like first identify equation of motion, and then from there you can start asking questions about like when you bottom out, how fast are you going? And like probably terminal velocity, whatever that number is, or close to it. Cool. Is that a wrap? We're like ready? Maybe? Perhaps. It looks good, feels good. Anything else? All right, we can call it. Say this is quiz, something like this is quiz number 3. We'll have like some angle, some damping quality, some mass, and we can kind of figure out from there all the other steps. All right, thanks a lot.